Welcome viewers to the third segment of the seventh lecture for the online series of lectures for the course of linear algebra. Towards the end of the previous segment, we were trying to prove theorem 2, the rank-nullity theorem, and there we proved that the range of the linear transformation T is the span of these n minus k vectors. Now, we will try to prove that these n minus k vectors are actually linearly independent. Okay, so let's prove that these n minus k vectors are linearly independent. Suppose the sum of the terms Ci, T, Ui, okay, as I runs from k plus 1 to n is equal to the zero vector of the vector space W for scalars Ci in the ground field F, where I is between k plus 1 and n. Okay, so we set an arbitrary linear combination of these n minus k vectors T, Ui to be the zero vector of the vector space W. Okay, now by the linearity of the transformation T, we immediately see that it can be written down as T of these sum is equal to the zero vector of the vector space W. Hence, from the definition of the null space of a linear transformation, we see that the vector given by this linear combination is in the null space of T. Okay, good. Let me erase this stuff. Okay, but according to the hypothesis, this is an order basis of kernel of T, right? And since V is a vector in kernel of T, we should be able to write V as a linear combination of these k vectors, which we write now. V is equal to sum of the expressions Bi, Ui as I runs from 1 to k, okay, where the coefficients of linear combinations are Bi's. Okay, so now this and these together give us sum of all the expressions Bi, Ui as I runs from 1 to k is equal to sum of all the expressions Ci, Ui as I runs from k plus 1 to n, and we bring everything on one side, and since all these Ui's are vectors in the vector space V, we must have the sum of all the expressions BIUI plus sum of all the expressions CIUI is equal to the 0 vector in the vector space V. Now we know that this is a basis of V, right? A basis of the vector space V. So it must be a linearly independent set, and hence these coefficients B1, B2 all the way up to Bk is equal to Ck plus 1 is equal to Ck plus 2 all the way up to Cn is equal to 0, right? So all these coefficients are identically 0. So so we have seen that. So what did we start with? We start with this expression. Remember, we start with CIT UI I equal to k plus 1 to n is equal to this. And a while ago we just saw that all these coefficients are 0. Ck plus 1 equal to Ck plus 2 all the way up to Cn is equal to 0. So now it implies that these vectors T uk plus 1, T uk plus 2 all the way up to TUN, the set is a linearly independent set. Linearly independent set. Previously we saw that RT is the span of these n minus k vectors T uk plus 1 all the way up to TUN. And now we see that these vectors are also this set is a linearly independent set as well, which means that these forms a basis of the range of the linear transformation T. So this is a basis of RT. Okay, so which means that the rank of the map T, rank of T is equal to how many vectors are there in this set? N minus k, right? So we denote the rank by R. We get R equal to n minus k. Okay, so where k is the nullity of the linear transformation T, since u1, u2 all the way up to uk, this set was taken to be the basis of the null space of T or the kernel of T. So it boils down to the fact that R plus K is equal to N, meaning that dimension of V is equal to the the rank of T plus the nullity of T, QED. Now I suggest a few exercises for you. It's important that you work out these exercises, okay? If you have any question about the exercises that I am suggesting here, we can discuss them on Slack, or you can call me privately if you want. Page 73 from our textbook, problem 2, 3, 7, 8, and 13. Okay, good. Now the notion of the algebra of linear transformations. We'll now get to the notion of linear algebra. The algebra of linear transformations. Okay, so given two vector spaces V and W over the same ground field F, so we have two vector spaces, both are defined over the same ground field F. The set of linear transformations from V to W. Okay, so we have studied properties of a linear transformation from our vector space V to another vector space W. Both are defined over the same ground field F. Okay. Now, if I take the set of all possible linear transformations from the given vector spaces V and W, from the given vector space V to the to another vector space W over the same ground field F, then these set can be seen to possess the structure of a vector space. Now, as a specific example, one can focus in the situation when V and W are the same. That is, we focus on the set of all linear transformations from the vector space V to itself. Okay, these set, contrary to the previous set when V and W are taken to be different, has more structure in it, more structure than the structure of a mere vector space. Okay, we'll see that we can, when we take V and W to be the same, then the set of linear transformations from the vector space V to itself in this set we can talk about composing linear transformations, meaning that we can take product of two such linear transformations from the vector space V to itself. Okay, so in a vector space we don't have the notion of the product between two vectors, but when we endow the set of vector space to with this additional structure of taking product of elements in a compatible way subject to some nice properties, we call it a linear algebra. Okay, so in the special case when V is equal to W, so that we are concerned with all the linear transformations from the vector space V to itself, it can be endowed with the structure of a linear algebra. Okay, so in this part, for the rest of the part of lecture 7, we'll be discussing various properties of the linear algebraic structure of this set of linear transformations from the vector space V to itself. Okay, so for this we open a discussion with a theorem which we call theorem 3. Let V and W be vector spaces over the same field F, spaces over F. So now, first of all, when V and W are taken to be different in general, we take the set of the linear transformations from the vector space V to W, and we discuss the vector space structure of this set in theorem 3. Okay, let T and U be linear transformations from V to W. The function T plus U, which is supposed to be a function from V to W as well. Okay, so now this is a function from V to W. So how does it act on a given vector V of the vector space V? This is how we define it. This is defined as T of V plus U of V for all V in the vector space V. Okay, we number this by equation number 18. Okay, and this is we need to show that this is a linear transformation. The statement tells us that the function T plus U defined in this way is a linear transformation from V to W. Now, if C is a scalar, okay, C is taking value from the common ground field of both the vector spaces V and W. Okay, the function, so we can define a function C times T, okay, which will be a linear map from the vector space V to W, defined by CT. So CT will be a linear map, and that the action of this guy on a vector V is defined as C times T of V. T of V is a vector, and that vector gets multiplied with C to give a new vector in the vector space W, right? For all V in the vector space V. This is our equation number 19. So defined by this is a linear transformation from V to W. Okay, now the set of all linear transformations from V to W equipped with vector addition like this and scalar multiplication like this is a vector space over the same field F. Okay, so let me write it. The set of all linear transformations from V to W equipped with a vector addition. So now the vectors in this vector space will be these functions, okay, equipped with vector addition. This one is a vector addition and scalar multiplication as given in 18 and 19 is a vector space over the same ground field F. Okay, so this is theorem 3. So I'll sketch the proof of this theorem now. Proof of theorem 3. So first of all, given two linear transformations T and U from V to W, one defines their addition according to equation number 18. Okay. So if VW are two vectors in the vector space V and C is any scalar, then T plus U acting on this a vector CV plus W, okay, is equal to T of CV plus W plus U of CV plus W according to the definition 18, equation number 18. Okay, one can write it this way. Now this is equal to C TV plus TW, right, by linearity of T, and plus C times U of V plus U of W, right? And this we can do using linearity of T and U. So now we gather the terms containing C in their expressions. We arrive at C of TV plus UV, right? And TW plus UW. Okay, why can we do that? Because TV and UV are both in the vector space W and C is in F, and we know that W is a vector space over the ground field F, so we can write it. Okay, now this will be equal to, according to the definition of addition of two such functions given by equation 18. This gives us c times t plus big U acting on V plus t plus U acting on the vector W. This we can do using 18. Okay, proving that t plus U is indeed, so this guy is equal to this, proves that t plus U is indeed a linear transformation. Transformation from V to W. Okay, good. Now for VW in the vector space V and CD in the field F, CT acting on this vector dV plus W. Okay, is equal to C times T of dV plus W. This we can do using the definition of scalar multiplication on the set of linear transformations from V to W using 19. Okay, and this is equal to dTV plus TW. This we can do using linearity of T. Linearity of T. Okay, so I need some space. So CT acting on dV plus W is equal to, now from here we see that this is equal to CD times TV plus CTW. Why is it so? Since TV is TV, both TV and TW are in the vector space W and CD are scalars, and we know that W is an F vector space, or W is a vector space defined over the ground field F. W is an F vector space. Okay, so C times D is the same as D times C, which follows from the property of a field. So this can be written as D times C times TV right, plus C times T of W, right? So from which we execute definition 19 again. This is CET as an operator, as a linear transformation from the vector space V to W that acts on the vector V, and again by the same token, C times T is the linear transformation on the vector space V, from the vector space V to the vector space W. So using definition 19, okay, so this guy is equal to this, which means that the transformation C times T is a linear transformation. Okay. Now I leave it as an exercise for you to show that with respect to the vector addition and scalar multiplication provided in equation number 18 and 19, the set of all linear transformations from the vector space V to the vector space W is going to satisfy all the axioms of a vector space listed in the beginning at the start of lecture 6. Okay, so let me write it for you that you need to verify. Verify that the set of all linear transformations from V to W with respect to a vector addition and scalar multiplication provided in equation number 18 and 19 satisfies all the vector space axioms. QED. So once you verify this, you will see that this is indeed an F vector space. Okay. All right. So we have to give a notation to this vector space. The set of all linear transformations from the vector space V to the vector space W is a vector space and is denoted by this symbol L. Okay. This is a vector space over F. They are both vector spaces over the same ground field F. So there is only one field in this picture, which is F. So all these three so there are three vector spaces. V is a vector space, W is a vector space, and LV comma W is another vector space. All these vector spaces are defined over the same ground field F. Okay. Now the case when we have both these vector spaces V and W to be finite dimensional, then LV comma W, or the vector space of all linear transformations from V to W, is also a finite dimensional vector space, and its dimension is m times n, given the dimension of V to be m and that of W to be n. So let me write it by means of a theorem whose proof will be omitted. Let V be an n-dimensional vector space over F, and W be an m-dimensional vector space over the same field F, the vector space LV comma W is finite dimensional as well, and has dimension n times n. Proof is omitted. Okay, good. Now the special case when V and W coincide with each other. Okay, so we for such a linear transformation we use a different name. If V is a vector space over the field F, a linear operator on V is a linear transformation from V to itself. So instead of saying that we have a linear transformation from V to itself, we'll just say that we have a linear operator on V. Okay, we'll save a few words by going to this new term, linear operator on a given vector space. Okay, now we have a theorem. So let me erase everything here and state this theorem and prove it. Theorem 5, which states that if we are given three vector spaces V, W and Z over the same field F, let V, W and Z be vector spaces over the field F, let T be a linear transformation formation. So we'll be defining composition using this theorem. T be a linear transformation from V to W, and U be a linear transformation from W to Z, then the composed function U composed with T acting on V is equal to U of T of V for all V in the vector space V is a linear transformation from V to Z. Okay, so let's prove it. Proof: given a scalar C and a pair of vectors VW in the vector space V, we write U composed with T acting on this vector CV plus W is equal to, according to the definition of composition, it's going to be U of T of CV plus W, right? Now we use the linearity of so it's the using the definition of composition. So this is equal to U of CTV plus TW, and we can do this since T is linear, right? Since T is linear, and this is equal to C of U of TV plus U of TW, right? U of T of W. Since U is linear. Now this is nothing by the definition of composition is going to be U composed with T acting on V plus U composed with T acting on W. Definition of composition. So what have we seen? We have seen that this guy is equal to this, which means that this map U composed with T defined by this is indeed a linear map from V to W. Sorry, V to Z, right? From V to Z, not V to W, V to Z. Okay, so from here to here and from here to here, therefore we have the composed map to be a linear map from V to Z. UT is a linear map from V to Z. QED. Now a remark following the definition of composition in Theorem 5. If one chooses in Theorem 5 V equal to W is equal to Z, so that both u and t are linear operators on V. One immediately finds that the composition one immediately finds that the composition U composed with T, or U times T, is a linear operator on V as well, is a linear operator on V as well. Okay. Thus the space L V comma V is the space of all linear operators on V, can be endowed with a multiplication with defined on it by composition. Okay, so if we have a linear operator here and we have another linear operator in the same space, same vector space, we can multiply two such vectors by composing them, composing one with the other. Okay, so if we have two linear operators T and U in this vector space, then Tu is not equal to Ut in general. Okay, they in general fail to commute. So also note that if T is in this vector space L V comma V, then one can form T square by composing T with itself or multiplying T with itself. Similarly, one can go on like this. T to the n is equal to the multiplication of T with itself n many times. And one defines T to the 0 to be the identity when T is not the 0 operator, which maps everything to the 0 vector of the vector space V. Okay, so this was the remark. Now we have a small lemma. This composition that we just defined, okay, for the case of a vector space, the composition between linear operators on a vector space V. So there are some nice properties satisfied by multiplication or composition of operators on a vector space. So let me list out these properties in this lemma. Lemma 1. Let V be a vector space over F. Let U T1 and T2 be linear operators On the vector space V, let C be a scalar. Then the following hold: I times U. um, we write composition by means of multiplication. I times U is the same as U times I is equal to U. B, U times T1 plus T2 is equal to U times T1 plus U times T2. Also T1 plus T2 times U is equal to T1U plus T2U. C times U times T1 is equal to Cu times T1 plus U times Ct, sorry, is equal to U times Ct1. Okay, so these are the three nice properties here. I is the identity transformation on V. Identity transformation on V, that is IV is equal to V for all V in the vector space V. Okay, right, so here is the proof. I times U acting on V. Okay, this is the operator that we are looking at, and by the definition of composition it's going to be I of U of V, and then by the definition of identity transformation it's going to be U of V. So also if we do this, okay, then according to the definition of composition it's going to be U of I of V, and again invoking the definition of identity transformation it's going to be U of V. So this is equal to this and this is equal to this, and they hold, they are they hold for any vector V in the vector space V, so that we have IU to be equal to U to be equal to UI. So part A is proved this way. Now for part B, so we start with U of T1 plus T2 and let this operator on V act on the vector V. So by the definition of composition, this is U of T1 plus T2 acting on V, right? Using definition of composition. and this is equal to u of t1 of v plus t2 of v using 18 the vector space structure, the vector space structure of LVB, or to be more precise, the vector addition in this vector space, the rule of vector addition in this vector space. So now U is a linear operator, so using linearity of, so this is a vector in V, this is also a vector in V, so we can write it as U of T1V plus U of T2V, and since U is linear. Okay. All right. So therefore U of T1 plus T2 acting on V is equal to, again we use this definition of composition, U composed with T1 acting on V plus U composed with T2 acting on V using definition of composition. And U composed with T1 plus U composed with T2 acting on V using 18 back, because UT1, U composed with T1 and U composed with T2 are both in the vector space LV comma V, and we are just using the rule of addition in this vector space. So we end up with this U composed with T1 plus T2 is the same as UT1 plus UT2. Okay, now T1 plus T2 composed with U and this linear operator acting on the vector V gives us, by the definition of composition, using the definition of composition. Okay, and UV is just a vector, right, in the vector space V, and this is going to be T1 UV plus T2 UV. Using 18 again, where T1 and T2 are in L of V comma V T1 and T2 are linear operators on the vector space V. We are just adding these two linear operators in the vector space LV, V using equation number 18. Okay, good. Now, using the definition of composition, it can be written down as T1U acting on the vector V plus T2U acting on the vector V. So here, using the definition of composition, okay, and this is equal to T1U plus T2U acting on V, here using 18 BRAC, since T1U, both T1U and T2U are linear operators on the vector space V. So we can add them up using 18. So this was the left hand side and this is the right hand side, and since this equality holds for any V, we must have T1 plus T2 times U is the same as T1U plus T2U. Okay, so now for part C of the theorem, we have U, T1, T2 to be linear operators on the vector space V, and C is a scalar. So this guy is an F vector space given a vector V in the vector space V. One must have C times UT1 acting on the vector V is equal to C UT1 acting on V and okay, so I think I need a break at this point and I'll be back in a minute. Thank you for attending this third